Okay, that should be recording now. So last Saturday, unfortunately, the talk I gave wasn't recorded. Something corrupted or crashed with OBS, so I'm now doing these a little bit later. So anybody that missed the talk has the opportunity to see it recorded. So what did we discuss last session? We discussed the trigonometric functions, so we define them from right triangles, and we use the trig functions and the inverse trig functions to find the sides of right triangles as well as the angles of right triangles. We then generalized our ideas to any triangle whatsoever, and we did this using the sine rule and the cosine rule. And in fact, one thing that we found was that given any triangle, so this isn't necessarily a right triangle, if we know, I don't know, 3 pieces of information, let's say an angle, another angle, and then a side length, we could then use the sine and the cosine rule to find the other angles. In fact, well, here the interior angles sum to 180, and then you can use sort of the sine rules and cosine rules to find these other sides. There are 2 exceptions. One, for example, you can draw sort of 2 triangles with the same interior angles, so that's 3 pieces of information, but unfortunately that doesn't uniquely define a triangle, it just tells you triangles up to similarity, right? This is going to be a scale factor of another, so this got a side length A, this is going to have a side length Ka. And finally there was a situation, the ambiguous case, where if we knew this side and this side perhaps, and I don't know, maybe this angle, so a triangle with a side length of A and a side length of B and an angle X, well, you can find another triangle with a side length A, a side length B and an angle X. You can just take this triangle here, so now we have this triangle. But besides that, if you have 3 pieces of information, then everything's uniquely determined. And once we then knew how to find side lengths and angles of any triangle whatsoever, we could apply this to geometry. Obviously, you can break shapes into triangles and use just compound geometry. But also, we looked at things like, if you had a circle, how to find things like the area of the sector, or perhaps the area of a segment. This is a segment and this is a sector. And we also generalized a rule to find the area of a triangle given 2 sides and an angle. And finally, what we did in the last talk was look at the unit circle, where we had our previous notions of trigonometry, where I defined them using right triangles, and then we generalized the notion of what a trig function is, because we could define it for any angles, not just angles between 0 and 90 degrees, or for the rest of the talk I'm going to be talking in radians, so 90 degrees is of course pi over 2 radians. So I hope my waffling hasn't distracted you too much, because in this section, I gave the talk in one fell swoop, but I want to break this up into graphs for one talk and identities for another. So this is going to be a talk about the graphs of trigonometric functions. Why do I want to talk about graphs? Well, graphs are a useful tool in mathematics to sort of give you a bit more intuition behind both geometric but moreover algebraic problems. So our goal for this session is to be able to do problems like, I don't know, sine of x equals a half. And we want to find all the values of x within a certain range, I don't know, all the values of x between 0 and 4 pi. And we want to find all the values of x such that this is true. And the way we're going to do this is we're going to, once we understand the graph, we'll be able to apply the inverse trig function and then use the graph and the symmetries to look at other points. But I digress, we'll get to that. So if we're going to be talking about functions, if we're going to be talking about graphs of functions, then we need to talk about functions. So this is a recap for those that may be a bit rusty. So what is a function? A function is a binary relation between 2 sets A and B. What does that mean? Well, it's a description of sorts where you take something from the input set, so this is called the domain, so you have an input, and it takes it to an output. The collection of all outputs is called the range. So I like to think of functions in essence as a machine of sorts. So you can think of like a computer program or some set of steps in order to get to an output, a series of steps, if you will. And perhaps, so in this function, let's say we input the value 2, the function is going to take 2, apply some sort of algorithm, and it's going to then output the number 4. And the reason why this is binary relation is because we have two parts, an input and an output, and the function relates the two. I will mention one thing which I've actually put down here, is that a function cannot produce two different outputs from the same input. So it's like if you have an algorithm, let's say, and you input 2 and it gets 4, you can't then input 2 again to the same algorithm and somehow get a different output. It will always end in 4. So if you have some sort of description of a map where, I don't know, f of 2 equals 4, but also f of 2 equals 3, then this isn't a function. This breaks our rule. However, as you can see in this description, we have two values that map to 1. So -1 goes to 1, and +1 also goes to 1. This is perfectly fine. Two inputs can map to the same output. So let's do a brief example just to illustrate some notation. So here we have f of x equals x squared. And this is a function with a domain, and I've given you a collection of numbers here. And the question asks, what is the range of f? Well, let's do some notation here. Let's do f of -2. So I'm evaluating the function at -2, which is one of our inputs here. And in this situation, here we've got x equals -2. So if x equals -2, then our function equals x squared, which is -2 squared, and this is of course equal to 4. Similarly, I can take this input, the next one, and compute the function at -1. Notice how x equals -1 in this case, so we have -1 squared, which of course is equal to 1. And we can do this for all the inputs in our domain. This is precisely how you actually find the range. And you can see it's just the squaring function. So -2 maps to 4, -1 maps to 1, 0 maps to 0, 1, well, 1 squared is 1, 2 squared is 4, and 3 squared is, of course, 9. So you'll see this a few more times where we basically take a sample of points from the domain, and we then calculate the function at those points. So now we know what a function is. We can now describe what the graph of a function is. Now, graph of a function f of x is the collection of ordered pairs, basically where your x-coordinate is the input and the y-coordinate is the output. And the graph is when you do this for all the inputs in the domain. Now, obviously, if you have a domain which is infinite, such as, I don't know, x is all the numbers between -2 and 3, of course, you can't just simply list all the pairs. That's impossible. You can't list infinitely many things. But what you can do is you can plot them. So here's an example. Plot the graph f of x equals x squared. So this is our function from earlier. Between this interval, -2 and 3. So the way you do this is you take samples from this interval, which we've done here. We've taken -2, -1, 0, 1, 2, and 3. And this essentially just partitions our interval here. And so now what we want to do is collect those pairs. So we have -2 paired with 4, -1 paired with 1, 0 paired with 0, 1 and 1, 2 and 4, etc. We plot them on our diagram. So here's -2, this goes up to 1, 2, 3, and 4, so this goes here. -1 and 1, well, we're going -1 in this direction in the left, and then we're going up 1. You have 0 and 0, which puts us here. You have 1, 1, 2, 4, And of course, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's going to bring us up here. And why did we take a sample? Well, we can kind of see what this function's supposed to look like. If we did it for all the values in between, it sort of looks like if you connect the dots, it almost looks like you have this cup shape, or this U shape, if you will. And that's our graph sketched. It's customary for functions to label all the points at which it intersects the x, and this is called the y-axis, but I've labeled it f, and to label all the points at which it's intersecting. So this is 0, 0. So I've probably shown you guys how to suck eggs here, because really and truthfully I'm expecting you to know how to do this, but that was just a brief recap. Some functions which you guys should be familiar with. So for example, we have a function y equals 2x minus 1. Here the negative 1 describes how this line intersects the y-axis, and the 2 in front of the x describes the slope. So as you go along 1, you go up 2. Similarly here, we have a y-intersect of plus 2, so this is going to intersect the graph at y equals 2. But we have a slope of negative 1/2, so every 1 along we go, let's go 1 along, we go down 1/2. And generally speaking, lines will take this form: y equal mx plus c, where m is your slope and c is your y-intersect. Now, how do we know it's a y-intersect? Well, when the function is at the y-axis, this is exactly when x equals 0. See, we're along the x-axis, we're at the point x equals 0, and so whenever you hit the y-axis, x equals 0. And so to find out where the function hits the y-axis, you set x equals to 0. So y equals m0 plus c, well, anything, of course, times 0 is 0. So this is going to be equal to c. And so the y-intercept is, of course, this value c. But that should be familiar. It's also customary to, again, label the graphs where it intersects these axes. Also, these are perpendicular, so often it's nice to put a little notion of, hey, this is a right angle. We've also got quadratics. I'm not going to go through these in as much detail, just I sort of expect you guys to know anyway, but here we have a quadratic equation. I've factored it into a product of linear terms, and so when does this equal 0? So when does the y equal 0, which of course is exactly when you intersect the x-axis. Well, this is going to equal 0 when x equals 2, or when x equals negative 1. And you can see that we've intersected here. And similarly, if you plug in x equals 0, so that's going to be minus 2 times 1, it will give you the y-intercept. It's also customary to plot, sometimes when you have a maximum or a minimum, it's customary to plot this. Do I want to go through how to do that? If you've never heard of completing the square before, then you can zone out for a brief moment, but the way you find the maximum and min, a nice way, is to complete the square. So we have our quadratic here, and a trick to use is to just, well, x minus or plus half of this, which is going to be minus 1/2. You square that. And notice here, if you were to expand this, you get x squared minus x plus 1/4. Now the quarter just doesn't match up at all, but these other values do. And so to correct this, we subtract from here enough to get to here. So this is going to be minus 9/4. Okay? And then, well, I mean, so why does this help us find the minimum or the maximum? Well, notice that here we've got the square function. And the square function is always positive. In fact, it's always positive except for one point where it's equal to 0. And so this is equal to 0 at x equals 1/2. And so if this is always positive, then this thing is minimized when this is equal to 0, which of course would then leave you with just negative 9/4. So this value here is 1/2, and then negative 9/4, and this is our minimum point here. And we've also got something called a reciprocal graph, which we'll look at later. But here, notice that we haven't intersected any axes, but we can put a point of reference. So here I've just labelled the point 1, 1, which we know is on the graph, because if we plug in x equals 1, we get y equals 1. It's also customary, you can see the graph is increasing and increasing and increasing, but never touching the y-axis. So it's also useful to just note that this graph has two what we call asymptotes. These are equations of lines which the function approaches but never touches, and these asymptotes are of course when x equals 0 and y equals 0. These are the axes. The axes of the function are the asymptotes. Okay, so that's probably quite a thorough review for what I'm intending to introduce next. So in the last session, we showed how the unit circle, you can use trig to find the point, and moreover hinted at the fact that you can use the unit circle to define the trig functions for any angle, not necessarily just between 0 and pi on 2. I think my explanation last video was somewhat poor, so I'll give another go at trying to explain this. But here we have a unit circle. So that means it's a circle of radius 1, and it's centered at the origin. So this is the point 0, 0. Now, when we describe this sort of rotation, as we will, we go from the positive x-axis and we go anti-clockwise. And so you can kind of, if you use trigonometry on this right triangle, you will get that the coordinates of this point, right, the x-axis, the width is the cosine, and the height, which is the y-coordinate, is the sine. This is why it is more natural to go anti-clockwise instead of counterclockwise. Sorry, to go anti-clockwise rather than clockwise, because if we went the other way, then on our right triangle, for a small angle that we could compute for the triangle, we'd have a negative height. The sine coordinate would be negative. But of course, now we have this notion, we can generalize sine and cosine functions by saying, well, what would perhaps the angle be if we were to go more than 90 degrees? How would we compute cosine and sine of this value phi? Well, what you do is you just look at the coordinates of this point. So this is going to be cosine phi, and this is going to be sine of phi. I'm omitting the brackets here, but it's conventional. And so if you wanted to, let's say, calculate, I don't know, this somewhat looks like 135 degrees, or, yeah, I'm not going to convert that to radians. You could almost draw the unit circle and use a ruler to measure the height, but you could also draw a little triangle. Now this angle here won't be phi, it will be 180 minus phi. But that gives you then a little triangle which you can then find the height and find the width. The width will be positive for the triangle, but the coordinate, the width, will be negative. So we know in this sort of second quadrant, one of 4 pieces, the second quadrant, the cosine is negative. So let's do an example. I think I did this example in the last talk, but I'm going to do it anyway again. So calculate sine of 7 pi over 4 and cosine. So really and truthfully what we're doing is we're drawing a unit circle. We are then going an angle 7 pi over 4, which is this angle here. So this is 7 pi over 4. And we want to find this coordinate, because this coordinate will tell us what the sine and cosine function is. That's in fact what their definition is. That's a really poorly drawn 4. How will we do this? Well, we'll actually draw this little triangle here. So this is going to be a right triangle, and we want to find this angle. Well, the whole rotation is 2 pi. And we've gone around 7 over 4 pi. So this little angle is going to be 2 pi minus 7 over 4 pi, which is going to be 1 over 4 pi. Okay, So this, if we draw the triangle, we now have a right triangle with an angle of pi over 4, and we have a radius of 1 because it's a unit circle, and so we now want to find the height and the width. Well, the width is going to be the cosine of pi over 4, and the height is going to be sine of pi over 4. Now, there's a couple of ways you can do this. You could plug it into the calculator, and that's perfectly fine. Remember to plug in to select radians if you're using pi over 4, or degrees if you're using 45 degrees. But remember that we also have these triangles we're familiar with. This 45 degree, 1, 1, square root of 2. So if the radius, it's not the radius, well, yeah, the radius is 1, so the hypotenuse is 1. Well, if we divide all the sides of the triangle by square root of 2, so we get 1, this is still 45 degrees, but here we have 1 over square root of 2 and 1 over square root of 2. So this is just a way to calculate what these are. So this length is 1 over the square root of 2, this length is also 1 over square root of 2. So we're almost done. We've now got this triangle. We know that this height over here is 1 over square root of 2, and we know that this width over here is 1 over square root of 2. So our coordinates is going to be 1 over square root of 2, but then negative 1 over square root of 2. Why? Well, look at the coordinate. We're below the x-axis. We're in the negative y coordinates. So this is going to be negative. Whereas we're in the positive x-axis, so this is going to be positive. And in fact, there's symmetry here. In each of these situations, this is going to be pi on 4. Pi on 4. This is going to be 3 pi on 4. This is going to be, and so on. We've got some sort of symmetry. This is you can sort of see how they're just sort of reflections of one another. But I digress. So we have these values. If I use the eraser and take out here, and I plug in that, notice how this angle is pi on 4, this angle is 3 pi on 4. Here we're going to have our width is negative and our height, the height here is positive. So the width is negative and the height is also negative. So we have this nice symmetry. What's this? Well, this is pi plus pi on 4, so that's going to be 5 pi over 4. 5 pi over 4. At this point, we've already calculated what these are. This is the coordinate here, negative 1 over square root of 2, and over here this is that. But we can also figure out what the other angles are down here in the second question. Notice that at sine equals 0, if we draw the unit circle again, what is the sine of 0? Well, it's the coordinate when your angle 0. Well, the coordinate when your angle 0 is this, which lies on the radius, on the circumference. Remember that the radius is 1. So this coordinate here is simply 1, 0. And the way we've defined the unit circle is the x-coordinate is always going to be cosine, and the y-coordinate is always going to be sine. So sine of 0 is 0. That's going to be 0. Sine of pi over 4, this angle is pi over 4, and our height using our symmetry method is, why have I got a negative there? That shouldn't be negative, our height's positive. Our height over here is 1 over the square root of 2. And similarly, pi over 2, well, that's going to be the right angle up here. And so this is going to have coordinates 0, 1. So our sine is going to be the second coordinate, so that's going to be 1. Here we get 1 over 2 again, if we look at the triangle. And you can fill these out. If you have sort of the whole pi, then this is going to be negative 1, 0. So this is, of course, going to be 0. And then you've got symmetry, negative 1 over square root of 2, and then 0 again. So we can plot these points on the graph. So again, we're doing exactly what we've done before. We've taken a sample of points within this interval in order to graph sine of theta, sorry. So we've taken our sample and we can plot these points. So initially you might have just plotted, you might not have plotted these intermediate points, you've just plotted 0, pi on 2 is 1, pi is 0, 3 pi on 2 is -1. But with these points, it's sort of uncertain, like maybe they're straight lines, maybe that's how you connect the dots. Perhaps they're not straight lines, perhaps they concave inwards, and that's how you connect the dots. Or perhaps they go outwards, they sort of convex and they go outwards, and you have this sort of sine wave. Well, I mean, it gives it away. You do have a sine wave, don't you? And the way you sort of figure this out is what is 1 over the square root of 2? Well, it's a little bit more than a half, so it's going to be roughly about there. And similarly here, it's going to be a little bit less than a half, negative a half. And now once you connect the dots, you get, excuse my poor drawing, you get this sort of sine wave. And there's a couple of observations you can immediately make about this graph. You might not think they're relevant observations, but they're observations you can make. So notice how, again, sine and cosine are the coordinates of the unit circle when you go along by an angle theta. But if you do the same angle, let's change this to green. If you do the same angle theta plus 2 pi, so you've gone all the way around once and then gone theta again, notice how you still end up in the same point here. That if you plus 2 pi, you will get the same coordinates. And that corresponds to this graph will repeat every 2 pi. So it'll look like this. You have one iteration, you have a second iteration, a third iteration, and it just continuously keeps going like this. And similarly backwards. So it repeats every 2 pi. It has a period of 2 pi. Second of all, you can identify immediately what the minimum and maximum are. The maximum is, of course, 1, and the minimum is -1. How do we know this? Well, again, look at the unit circle. Sine is the height of this coordinate. Well, this coordinate never exceeds 1 because it's a unit circle with radius 1. We can observe that this function intersects it's the x-axis, but in this case our input is theta. It intersects at 0, at pi, at 2 pi, and now since it repeats, right, 0, pi, 2 pi, well, since it repeats again, we just add another pi, so that's 3 pi, 4 pi, 5 pi. So actually, and similarly negative pi and negative 2 pi. The zeros are at integer multiples of pi. And finally, we can look at something called reflectional symmetries. What do I mean by this? Well, if you just draw a line down here, or rather, let's draw a line down here. Notice how you can reflect the graph over the line, and it doesn't do anything. Right? It's symmetric about this line. And it's the same true here. In fact, if you reflect over any maximum or minimum, the graph remains unchanged. It's a symmetry. So we have reflectional symmetries at these points. Okay. So what to take away from this? In other words, what is the graph of sine? The graph of sine is simply this sort of wavy function that starts at 0, goes up and down between 1 and -1, and it does this at sort of, you can go multiples of pi over 2, really. So we can do the exact same for cosine, or cos function. I'm not going to derive it due to time, but we can sort of notice the same sort of features. In this case, it starts at 1, because if you look at the unit circle and the value at 0 when the angle 0, well, this coordinate's going to be 1, 0. This was our sine. Well, the x-coordinate is our cosine. So it starts at 1, and then it goes down and up and down. repeats every 2 pi again by the exact same argument. So when you go around by 2 pi, you're stepping on yourselves, you're tracing your steps. Minimums and maximums are at 1 and -1. The zeros now are at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and similarly negative pi over 2, and so on. And the reflectional symmetries are now along sort of at 0, at pi, at 2 pi, 3 pi, 4 pi. So if you look at the sine function, notice how the zeros here are the reflectional symmetries here, and that the reflectional symmetries for the sine are the zeros of the cosine. So they've somehow swapped. Now, how do we graph the tangent function? Now, in the talk, I omitted this due to time. I'm just thinking if I want to go through it. Well, we recall from the previous talk that the tangent function is, well, tan is sine over cosine, but moreover, it describes the slope. So remember, the slope is sort of the change in y divided by the change in x. So this is slope. And this tells you how much you go up or down, given you go along 1 unit. Well, if you take the slope here, so we have a slope cosine of sine and so on, so the height's going to be sine minus 0, and the difference in width is going to be cosine minus 0, and this is then going to be sine over cosine, which is, of course, our tangent function. So the tangent function gives you the slope of the line as you increase with theta. So why is that important? Well, you can kind of now start picking your interval here with the unit circle. When your angle's 0, you have just this straight line here. The slope of this straight line is going to be 0. But now when you take sort of the midpoint here, if you will, if you bisect this angle, so if you bisect this right angle, you then get 45 degrees or pi over 4. And this slope, every 1 along you go up 1. And similarly, you can bisect this angle, and now this has a slope of 2, as you illustrated here. And you can bisect this angle, and you get a slope of 4. And you can keep sort of like tracing in. If you like make the circle bigger, you can sort of notice how I'm doing this, and then bisect, and then bisect, and the slope is getting exponentially larger, and it's getting exponentially larger until you get to a right angle, in which case, what's the slope of this vertical line? Well, the slope of this vertical line is infinity. And this is portrayed by the tangent function. As you can kind of see, we are starting at 0, and then we're just getting exponentially larger. But notice, when you then shift this way slightly, you now have a line that's going downwards. Right? It's now going downwards. So we actually then quickly go to negative infinity, and then we slowly get a lesser and lesser slope of the line. And that's where the tangent function comes from. But if there's anything to take away, it's that the sine function looks like this, the cosine function looks like this, and the tangent function looks like this. One interesting thing to point out is that this repeats every pi unit, whereas the cosine and sine repeated every 2 pi. So somehow by dividing a 2 pi periodic function by a 2 pi periodic function, we've now got a 1 pi periodic function. Our minimums and maximums are plus or minus infinity because we sort of zoop off to infinity and zoop down to negative infinity. Oh, excuse me. And this sort of corresponds to like when our asymptotes. Well, if you have sine over cos, it's going to go off to infinity when your denominator equals 0, and the cosine equals 0 precisely when we have pi over 2, 3 pi over 2, 5 pi over 2. So when you divide by 0, you go off to infinity. And similarly, this function equals 0 precisely when the sine function equals 0. The sine function equals 0 at 0, pi, 2 pi, and that's precisely we got 0, pi, negative pi, 2 pi, and so on. So I hope that makes sense. So obviously, in the first section, not only did we talk about the trig functions, but we talked about the inverse trig functions. So how do we graph those? Well, unfortunately, the inverse functions made sense when we talked about right triangles, because the angle here, let's say this angle, would be between 0 and our right angle, which was pi over 2, or 90 degrees, right? This angle couldn't be any more than 90 degrees, otherwise the sum of the interior angles would exceed 180 or pi. So in this region, we could actually invert the trig functions. But there's an issue when we actually try and invert it for general points between negative infinity and infinity. So we'll need a test to see whether a function is invertible. So here I'll define this terminology. A function is called one-to-one if no two inputs map to the same output. So remember back when we had our little sort of function machine, and I said that you couldn't input one value and have it input to multiple values. It just that doesn't work. We're not allowed that for functions. However, I did say that you can take two values and have them both map to the same output. Like that was allowed for some reason. Well, a one-to-one function doesn't allow this. Every input has to map to a unique output. So let's look at these functions. I'm only going to look at 2 and 3 just to save on time. I should probably look at 4 as well. So remember the graph of which we drew for the y equals x squared from negative 2 to 3. It looks something like this. So we want to decide whether this is a one-to-one function, or in other words, we want to decide do two inputs map to the same output. Remember, the outputs of course are our y-axis, and our inputs are of course our x-axis. Well, the answer is, if we sort of draw this horizontal line, so this is the line, I don't know, y equals 1. Notice how we intersect this red curve, at y equals x squared, at 2 points. So here, well, it turns out that this is negative 1 and 1, but you might not know that a priori, but it doesn't matter. Here we found two values, 1 and negative 1, that map to the same output, which isn't allowed for a one-to-one function. This is 2-to-1, if you will. So here, our value 2 isn't one-to-one. But notice on our second situation, we've actually restricted the domain to 0 to 3. And now no matter where we draw our horizontal line, we will only ever intersect 1 or no values. In fact, here if we pick, I don't know, our horizontal line to be y equals negative 1, well, this isn't in this isn't in the range, it isn't in the output of this function. So in fact, if you draw horizontal lines strictly when they're in the range, so the outputs, then it will exactly intersect the curve once and only once. And so here, tick. Now what about the sine function? I mentioned how taking the inverse, graphing the inverse sine function has an issue. And that issue is because instead of looking at sort of between 0 and pi over 2, we're now looking at all the infinite values of theta, the angle. And this is precisely why, like, if you were to graph the sine function, so remember we just graphed this, it looks like this, and we draw a horizontal line, let's say this, we intersect the curve at lots and lots of points. Right, this is between 0 and 2 pi, so in fact we intersect the curve precisely, this is 2 pi, precisely twice. So now I can swap here, here, and here. So the sine function is not one-to-one on this range between 0 and 2 pi, because it intersects it twice, meaning that we can find two values here and here which map to the same output. So unfortunately, our sine function doesn't work. I've already mentioned the vertical line test. So now we know what one-to-one functions are. We can now introduce inverse functions. So remember when I talked about sort of sine of the angle equals, I don't know, opposite over adjacent. So this is kind of our input is the angle, our output is this ratio. And I motivated the inverse sine function as doing the opposite way around, like given the output, give me the input. So here our function takes 0 to 0, and so our inverse function will go, okay, well, we'll take it back to the input. Our new input is the range, and our new outputs are the domain of f. And so I've made a note here, for inverses to exist, a function must be one-to-one. Why? Well, if you had, I don't know, in this situation, you have the square function, so that would take -2 and 2 to the same value here, right? It will take both of them to 4. So this is 2-to-1, which is fine, that's allowed for a function. But for the inverse function to exist, we need to be able to take the output and map it back to the input, which would mean this would send it to both 2 and -2. But that's not allowed for functions. We can't have one input mapping to multiple output. This doesn't work. We're not allowed this. And so, in order for the functions to be well defined, we need the property of things being one-to-one. So now we've got an example. Find the inverse of f of x equals 2x on this interval. There's several ways to go about doing this. So I've taken samples again. Here the input is 0, 1, 2, 3, and 4. So if you notice, this is just multiplying by 2. So, I mean, well, f of 0 equals 2 times 0, which is 0. So you're just multiplying everything by 2. So we have when x equals 0, f of x equals 0. When x equals 1, f of x equals 2 times 1, which is 2. When x equals 2, f of x equals 2 times 2, which is 4. And then 6, and then 8. Now remember, inverse functions map outputs back to inputs. So here are our outputs, 0, 2, 4, 6, and 8. And we know that our we're going to map back to the inputs. So this is going to map, 0 is going to map back to 1, 2 is going to map to, 0 is going to map back to 0, 2 is going to map back to 1, 4 is going to map back to 2, 6 to 3, 8 to 4. And notice how this original function, we're just doubling everything. And so our inverse in the opposite direction is just halving everything. So here we're halving it. So it makes sense. We can sort of observe that our inverse function, f inverse, equals x over 2. But alternatively, we've kind of drawn, we do y equals f2. So this is again our function. I've just written it in a different way. So y equals f2. Alternatively, what you could do is, well, given the input, y is the output, but we can try and do it the opposite way round. So we could try and solve for x. So then given the input, I can tell you what the output is, or given the output, I can tell you what the input is. So if we divide both sides by 2, we then get x equals y over 2. And so now in this situation, given the output, we can then plug it into this equation and we get the input. We find the opposite direction. And so our inverse function, in fact, let me use a different variable. Our inverse function is y over 2. And I mean, similarly, like, let's do another example. Y equals f of x, x squared. For x is positive. If you take the square root of both sides, and you solve for x, you get y, the square root of y equals x. Notice that if this was negative, then the square root of x squared is actually equal to, well, this is called the absolute value, and the absolute value just makes whatever's in there positive. But in that case, it doesn't work. We haven't solved for x. So again, in this situation, we have x inverse y equals the square root. So it's a procedure for finding inverse functions. You just write the function y equals this thing here, and then you solve for x in terms of y, and that's your inverse function. Now let's plot these two graphs. In fact, let me graph it like that. Let's plot inverse being, so this is y equals x over 2, and this is of course y equals 2x. And if we plot them both on a y-axis, x-y-axis, then notice something interesting. So this is, again, this is plus 0 and plus 0, so our intersect for both of these is going to be 0. And the slope for here, we're going to go, every one along we go up 2, because 2 is the slope here. Every one along we go up 2. Here our slope is a half, so every one along we go up a half. So these are the graphs of these two lines. But notice how we have this symmetry over the line y equals x. If we reflect, we'll actually map we'll map the red line to the blue line, and similarly we'll map the blue line to the red line. And this is generally true. You can sort of see it actually. Do I want to? Yeah, I suppose. If you kind of like have some weird curly graph like that, and then you have another one like this, which is just a reflection over this half line, then we know that this inverse functions take outputs back to inputs. So if you have like this is the y, this is the original function, let's say, and it takes us here. Well, notice how if we then plug in this value here, which is probably closer to around this point, we now go up and it goes along here, and this length here is the same as this length here. But yeah, that wasn't particularly clear. I apologize for that. But it's generally true that if you have a graph of your function, then the inverse function will be a reflection over this half line. So now we have a procedure, right? If we're given a function y equals f of x, first of all, we can plot the function itself using our sampling method. We can restrict the function to a domain, so a collection of inputs, where our function is one-to-one. And then finally, we can reflect about this half line, and that will give us the graph of the inverse function. So I'll do an example here. Y equals sine inverse. So we know that, again, do I do all of them? We know that the sine graph looks like this. In fact, if we start at, yeah, it looks like this. So we sort of start at 0 and we go down and up and down and whatnot. But notice if we draw sort of a horizontal line, we intersect at multiple points, which means there are multiple inputs which correspond to the same output. So we need to restrict the domain so that it's one-to-one. So the way we do that is we sort of restrict it here. Because now, wherever we draw the line, our range is negative 1-to-1. So whenever we draw the line across our range, we will intersect our curve exactly once. So here, no matter where we draw the line, we will intersect the sine curve exactly once. So here, this is pi on 2, and here, this is negative pi on 2. So in fact, let me draw this a tad more clearly. So once we draw our restricted sine graph, it looks like this. And this is pi on 2. This is negative pi on 2. That's not our sine graph. Our sine graph looks like this. There we go. So this is our y equals f. Y equals sine of x. And our domain is the values between negative pi on 2 and pi on 2. So we do the third step, which is simply reflect about y equals x. So if we reflect about y equals x, this is sort of the, let's draw this bigger. We'll draw our y equals x line. And so we have our sine, which looks like this and this. Then our inverse will look precisely like this. Go up. Because it's a reflection over this half line. So our blue is the sine, and then our reflection is this red line. So notice how this is now pi on 2. And this is negative pi on 2. And this is 1. This is negative 1. Why? Because this is precisely what the reflection is. Because here this is pi on 2. Right, sine goes up until pi on 2, and that's the domain in which it's 1 to 1. And when you make this reflection, this becomes the height. And similarly, the maximum of sine is 1, and minimum is negative 1. So when you reflect that becomes the domain. So when you go from negative 1 to 1, our sine function becomes, our inverse sine function becomes this. So this is equal to y sine inverse x. Okay. I'll take a step back for a moment and just, do I think that's an adequate explanation? Again, what have we done? We've taken our sine function, we've restricted it to a domain where it is 1 to 1. Notice that it takes every value in its range exactly once. Then what we've done is we've drawn this half line and we've reflected the sine function. Right? We've reflected it, and the inverse is now this blue. Well, no, the inverse is this red. And so now we've just plotted the reflection, put on the points of which is this minimums and maximums, etc. And this is our inverse function. And you can do the same with cosine and tangent. I encourage you to have a go at those problems. So how are we doing on time? We've got reciprocal and so on. So I'll now start going through this quite quickly because I want to get to the actual the example I gave at the beginning of the lecture that we want to work towards solving. So the reciprocal function of f of x is 1 divided by f of x. So you basically, if you have a function, the reciprocal is just 1 over that function. However, when we do this, we need to be careful, because if this function equals 0 at any point, then our reciprocal will be dividing by 0 at that same point. So here we're sketching functions. Do I want to do this? Yes, okay, let's do question 2. So we're graphing this between negative 2 and 2. We can take a sample, let's say, I don't know, negative 2, negative 1, 0, 1, 2. We then look at our outputs. Well, negative 2 squared minus 1 is going to be 3. Negative 1 squared minus 1 is 0. 0 squared minus 1 is 1. Then we get 0. Then we get 3 again. So plotting these on here, we kind of get something that looks like this. Sort of badly drawn, but I digress. So this is 3, and this is negative 1. So let me just quickly draw the line y equals 1. So what happens now? Well, if I now look at the graph y equals 1 over x squared minus 1, and we do the same table, so this is going to be minus 2, minus 1, 0, 1, 2. Well, when we input the bottom, this is just going to give us 3, but then 1 over 3 is going to be a third. When we input the bottom, we're going to get 0, but, well, divided by 0 will then give us sort of zooming off to infinity. That's really badly drawn infinity. So we're dividing by 0, so just put infinity there. We have 0 there, we divide it by negative 1, so that's just going to give you negative 1, infinity, third again. But now let's look at the graph. So we can plot these points. And negative 2, we can get like a third. And then as we get towards 0, we're getting larger and larger and larger and larger and larger. But let's look at the graph. So you can kind of think of the reciprocal of this graph as taking every height and dividing it by 0. So if you're more than 1, sorry, not every height and divided by 0, excuse me, is taking every height and reciprocating it. So take this height here and then do 1 divided by this height. So if this is 3, then 1 over, then our reciprocal will be then a third. If this is 1, then our reciprocal will be 1. If this is a half, then our reciprocal will be 2. And notice how when you reciprocate points on this graph, if it's above this line y equals 1, then it's going to dip below. So what do I mean? Here, we're getting larger and larger and larger, and so when you divide by a very big number, you get a very small number. But as you get closer to this point, notice how anything divided by 1 is just itself. And as we get close to 0, we're then dividing by a smaller and smaller and smaller number, which then shoots off to sort of infinity because we're about to divide by 0. And similarly from this end, it's symmetric about this. So this large number 1 divided by this large number gives us a very small number. 1 divided by this number here, 1, gives us 1. And then as we get closer and closer to this point, 0, we're dividing by smaller and smaller numbers, so this is zooming off to infinity. But now here, from the other perspective, we're now dividing by a very, very small negative number. So this is actually, if you think about it, if you divide it by a very small negative number, then we're getting arbitrarily close to negative infinity. And then as we divide by negative 1, anything divided by negative 1 is just negative itself. So that'll give us negative 1. So 1 divided by negative 1 is negative 1. And then we sort of zoom off this way. So I hope that explanation is more of an example, gives you somewhat of an idea of how to sketch the reciprocal functions. You draw your lines y equal 1 and negative 1. And so if you're dividing something in this sort of region here, which is a very small number, then it's going to be outside. The closer it is to this x-axis, the larger it's going to be, because when you divide by a very small number, you get a very large number. And similarly, when you divide by something outside, 1 divided by this very large number gives you a very small number. And hence why you get this reciprocal graph here. So now let's introduce the reciprocal trig functions. We could have introduced this earlier when we defined sort of like, I don't know, cosine of x. And this gave us adjacent divided by the hypotenuse. Well, that was sort of arbitrary, wasn't it? Why adjacent divided by hypotenuse? I mentioned that it relates these two sides, but we could have just as easily defined it to be hypotenuse divided by adjacent. And so what the reciprocal trig functions do is they do it the other way around. So the hypotenuse divided by adjacent, which is actually equal to 1 over adjacent divided by hypotenuse. And this is, of course, equal to 1 over cosine. So that's why they're called the reciprocal trig functions, because they're technically just 1 over a trig function we've known before. And so here's a definition based off of right triangles, but since we can write this in terms of a cosine, which we've generalized to any angle whatsoever, we can therefore describe the secant, or sec function, as being for any input as well. So it's defined off of the cosine function. So this is the secant function, which is 1 over cos. This is the cosecant function, which is 1 over sine. And this is called the cotangent function, which is 1 over tan. And now we can immediately look at the graphs. We can do the same trick as we did up here. So this is another example. I've already drawn in our lines at 1 and -1. And so here, we're dividing by a very, very small positive number, which gives us a very, very large positive number. Here we're dividing by a still small, but not as small, so it gives us a still large, but not as large. And now we're dividing something close to 1, which gives us something close to 1, and when we divide by 1, we get 1. And similarly, when we now divide it by something slightly less than 1, we get something slightly more than 1. When we divide by something close to 0, but positive, we get something very, very large. And so when you connect these dots, you get this sort of dip. Oh, okay. My sketching there wasn't very good. There we go. Notice as we get close to 0 or pi, we're getting closer to dividing by 0, so we're actually getting closer to infinity. So in fact, these are actually asymptotes. But now notice here, we have a very, very small negative number. So that's going to be a very, very large negative number. Now we've got a sort of a somewhat small negative number, which gives us a somewhat large negative number. Here we get -1. Anything divided by -1 is just negative itself. So 1 divided by -1, when you reciprocate, gives you -1. And again, we can sort of do the exact same. Something very, very close to 0, but negative gives us a very, very large number, and so we can connect these dots again. And so on. Okay? So here we're doing 1 divided by a thing. And these are the graphs of the reciprocal trig functions. I mentioned about the unit circle, that you can extend these. In fact, all of these trig functions have some sort of geometrical significance when it comes to the unit circle. Many people will have this as a tattoo, which is quite interesting to see on Twitter. So we've seen where sine and cosine come from, but let's do an example. So notice now this is the tangent line to the circle. When I mean tangent, I mean if you have a circle and you draw a line that just touches the circle at one point and only one point on the circumference, it will actually be perpendicular to this radial line. So that's precisely what I've drawn. But let's look at this triangle here. Notice that this is a right triangle. This has 1, and that's again poorly drawn. This is the radius of the circle, so it has a length 1, and this is our angle. Well, let's try and find this length here. Notice how, well, this is going to be the longer side, the hypotenuse. This is going to be the adjacent side. So cos of the angle equals the adjacent, which is 1, divided by the hypotenuse, which we don't know. We want to solve for this length. So if we solve for the length, we multiply both sides by the hypotenuse, divide both sides by cos. The hypotenuse equals 1 over cos, which of course is equal to the secant function. And that's what this length here is. It's the secant. And so that's why it's down here. It's like, given any angle, you can then draw the tangent line, you get this triangle, and this length down here is called the secant. So although we've just defined that algebraically here, where we're just messing around with dividing, multiplying, adding, and so on, here we've defined it geometrically. Both significant. So finally, I've been talking about graphs all this time, with the promise that they are useful. We can use them as intuition as to how to solve algebraic problems and even geometric problems. So here's an example here. So sine of x equals x. So whenever you have something along the lines of, I don't know, f of x equals g of x, and you want to find values of x such this is true, this will correspond to, I don't know, perhaps you graph the f function like this, and you graph the g function like, I don't know, this. Then the values of x that this is true are precisely the values of x where these two graphs intersect. Okay? So here I've drawn y equals 1, and here is y equals x squared. So these two values, what when squared equals 1? Well, we have 1 and negative 1. And this is precisely those 2 points, and this is the points that satisfy here. So when I've got sine of x equals x, we'll notice that if we draw these two functions, sine looks like this. We can go to the negative direction as well. And y equals x looks like this. So the values at which sine of x equals x are precisely the values at which these two curves intersect. And if you zoom into this region, if you really, really zoom in, this sort of does that, and this sort of pokes out like this. So it only really intersects at the origin. It only intersects once. The origin is precisely the point x equals 0. So how do you solve this algebraic equation? Well, if you look at the graphs, the values at which this is true are the points where they intersect. Where do they intersect? Well, we can look at the graph and say, well, they only intersect at one point, and that point is x equals 0. In fact, if you look at these two graphs, the line graph seems somewhat close to the sine function within this sort of interval, within this circle. But as you go further out, they look nothing alike. And this is actually an approximation that's quite commonly used in mathematics. Sine of x can be approximated as x for small values of x. Oh, and I noticed up here the coordinate Cartesian plane links geometry and algebra. I've mentioned how you can use graphs and the look at graphs to help you with algebra problems. Well, there's actually this is a very algebraic description of sine of x, and this is a very geometric description. Similarly, if you have something like, I don't know, x squared plus y squared equals 1, well, if you graph this, this isn't a function, by the way, it's a map, but if you still graph it, you get a circle with radius 1. So we can describe geometrical objects using our algebra, and we can describe our algebra using very geometrical objects. And it's thanks to sort of René Descartes, a very famous philosopher and mathematician who came up with this Cartesian coordinate plane, allows us to study not just geometry and algebra, but something called coordinate geometry. It's a very beautiful area of mathematics that you can interchange between geometry and algebra to solve your problems, and modern mathematics just relies off of this completely. So it's a revolutionary example. I'm going to omit this example. It's a lovely trig question, but it doesn't have much to do with using graphs, so I'll omit it for now. So here we go. We have some problems. So let's do cosine first. So again, what does cosine look like? Well, we start at 1, and then we sort of go up and down and up and down and up and down. And we go between -1 and 1. And similarly, we can go in the opposite direction. So take a moment and just try and remind yourself, what are these points where they intersect the graphs? That's supposed to intersect here, by the way, but I digress. This point's going to be pi on 2, this point's going to be pi, this point's going to be 3 pi on 2, this point's going to be 2 pi, and etc, etc, etc. Here we're only we're interested between -infinity and infinity. So we're going to keep drawing this graph. So we want to find all the values at which cosine of x equals 1. So like before, we've drawn cosine of x, let's draw 1. Well, the graph of y equals 1 is this sort of constant graph here. And notice how this graph intersects the cosine at all these peaks, the maximums of the cosine, all the values of x such that this equals the cosine is maximum. Well, when does so in other words, this equation is true precisely when the cosine reaches its maximum. So what values of x does cosine reach its maximum? Well, it reaches the maximum here at 0, it reaches the maximum here at 2 pi, it reaches the maximum here at 4 pi, and similarly down here at negative 2 pi. And in fact, you can see by the graph, since, well, you know that it repeats every 2 pi, so since we know one maximum, well, 2 pi along is going to hit that same maximum, 2 pi along again is going to hit that same maximum. So the equation, I keep writing sine, so the equation cos of the angle equals 1 is true precisely when x equals any sort of even multiple of pi. Okay. So all these values ad infinitum. Another way of writing this is equals 2 k pi, for k equals negative 2, negative 1, 0, 1, 2, and so on. So that's how you can use it to solve this equation. We've just drawn the graphs, observed where they've intersected. In fact, we've used a bit of symmetry here. So let's do it again. The cosec. So here, cosec of x equals 2. Now, an interesting thing to note. So we have the graphs of our cosecants and whatnot. So we could just have this graph and then plot the points at which it equals 2 and then find all these intersections, but that's quite difficult. Instead, what I'm going to do is note that the cosec is 1 over sine is equal to 2. And if I multiply both sides by sine and divide both sides by 2, I get sine of x equals a half. So the points of which the cosecant of x equals 2 are exactly the same points as the sine equals a half. So now we can draw our sine function, and now we're wanting to do it between 0 and 4 pi. We draw our sine function. That's 1 period. That's 2 period, and that's supposed to intersect here, but I digress. Now we'll draw the line y equals a half. So that's along about halfway point here. And so immediately, within our interval 0 and 4 pi, we know that there are 4 intersections, right? 1, 2, 3, 4. In fact, let me try and draw this graph a little bit more carefully because I want the geometry to be obvious. Okay. And so we have our points sort of here, 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 and here. So what we can do immediately to find a solution is remember that if you have a function which takes sort of input to output, then the inverse function takes output to input. So we've already found one value of x such that this is true. This is sine of a half. It's good to use your calculator to figure out these things. I mean, it is a value which you should know off by heart, but if you don't know it, there's no shame using a calculator. So this is equal to pi over 6. Now this is what your calculator returns. It gives you the value pi on 6, which is this point here. This is pi on 6. But there are 3 other points where the sine function equals a half. So how do we find those? Because the calculator hasn't given it to us. Our inverse function, although it takes outputs back to inputs, has only given us one input, which gives us our wanted value. So the way we actually do this is we use the symmetry of the graph. So what do I mean by that? Well, remember that the sine function, if we sort of draw a line right down here, the sine function is symmetric about this line x equals pi over 2. It's symmetric about this line. What does that mean? Well, it means that this length here, right, this length here from 0 to pi on 6, this length which is pi on 6, is the same as this length here, because it's symmetry, right? So we know that this length is pi on 6. We know that this value, the intersection, is pi. So if we want to find this value here, our intersect, then we take pi minus this length, and we get our intersect. We get the value of x for which this is intersecting. And that value is, well, it's pi minus pi on 6, which is equal to 5 pi on 6. So that's our second value of x for which we get an intersection. And again, we've used symmetry. We've used the fact that the sine function is symmetric about pi over 2. We know that this length here is pi on 6, and that's our first solution. But by symmetry, our second solution will be pi on 6 units away from this intersection here, which is pi. So we just take this value pi, we subtract pi on 6 along, and we get our other intersection. Now, how do we find these two values here? Well, we use symmetry again. How do we do that? Well, I mean, we could reflect along this line, but let's do it a different way. Sine repeats every 2 pi units. This value here is 2 pi. Sine repeats every 2 pi units. Which means that, well, first of all, this length is the same and this length is the same. But also, you can just think, well, if this value here is a solution, then 2 pi units along is also going to be a solution. So this value here is literally just pi on 6 plus 2 pi. And that's going to be 13 pi over 6. And similarly, this value over here, well, we know that this is going to repeat every 2 pi units. So then when we go 2 pi units along, we've repeated and gone to our intersection again. So similarly, we now have a value of 5 pi over 6. We add 2 pi, we get to our intersection. So our intersection is, of course, 5 pi over 6 plus 2 pi. So we've shifted it along. And this gives us, that's going to be 12 plus 5, 17 over, I believe, no, over 6. 17 over 6 pi. And so using the graph and its symmetries, we've found all the values of x between 0 and 2 pi for which sine of x equals a half, which is exactly the same as when the cosecant equals 2. And this is precisely when x equals pi over 6. Pi equals 5 pi over 6. Why am I saying pi? X equals pi over 6. X equals 5 pi over 6. X equals 13 pi over 6, which is this value here. And finally, x equals 17 pi over 6. And this gives us all the solutions. So this was sort of quite a complicated example, and I encourage you to go back to the beginning and try and do it yourself without listening to me go through it. But it's an example of where we want to solve this equation, and we can use the graph to find out how many solutions we're looking for. We can use the calculator to find one of them, and then we use the symmetry of the graph to find all the other solutions. So I'm not going to do a tangent example. I encourage you to have a go at this, and then use the symmetries of the tangent function. I'll give you a head start. This is, if you square it both sides, tan squared of x equals 3. Well, that means the tan x equals the square root. Well, it will equal plus or minus the square root. But if you square it both sides, you're going to get 3. Well, the tangent function looks precisely like this. This is between pi, so this is pi over 2, so now we've got another thing like here. Like that. And now if I graph plus or minus the square root of 3, which is slightly more than 1, and negative, notice how there are 4 points, 1, 2, 3, 4, for which the tangent of x equals plus or minus the square root of 3, or similarly tan squared of x equals 3. Now you can solve this in 2 cases. You can do sort of tan of x equals the square root of 3, and you can do the other case where tan of x equals minus 3. And remember, you start this off by simply evaluating the inverse. So we take the output, and this will give you the input. So this will give you x. I'll let you calculate on that calculator. And similarly, tan of x inverse of tan inverse of the square root of 3, negative the square root of 3, will give you another value of x. And now the last thing left to do, you might know this value, or you might know this value. You then say you know this value of x, for which you have the intersection. To find this value, you then shift it by negative pi, because the tangent repeats every pi units. And similarly here, if you know this value, then you add a pi to get this value. I'm not going to go through transformations. I think this is more than enough to explain that we can use graphs to solve these algebraic problems, and it's a very powerful tool to build up intuition. And we'll even see later some examples where we'll be using graphs to understand when things are like positive or negative, when things intersect and don't intersect. It's very, very useful in mathematics, but I digress. Thank you for listening.